Yeah, so I'm Bobin from Polygon, and I'm going to talk about Miden VM and describe the architecture and how we think about generating zero knowledge proof and how we actually do it on Miden VM. So the first thing is just to set the context. I want to go over how there are different ways to think about programs. So the first that has been discussed a lot during this workshop is the circuit-based model, where a program is the circuit. So you take a program and you translate it into a circuit. The alternative approach is the virtual machine model, or you can think about it as a machine computation, where if you have a virtual machine, the program is actually just the input into the circuit. So you still have a circuit, but the program is the input into that circuit. So there are very two different models of thinking about how the computations work. And Miden is a virtual machine, so we're working in this virtual machine model. So let's talk a little bit about what exactly is a ZK virtual machine. So to start out, we start with just what is a regular virtual machine, or kind of a state machine of sorts. So you have initial state, you have some program that the machine executes to apply to that initial state, and you get the final state. In the context of the ZK virtual machine, you get a few more boxes around here. So the first thing you get is at the end of the execution, you get a proof. So that proof basically says that if you execute the program against the state, you get a different state, a new state. The other thing that you get is your ability to provide a witness. This is like a non-deterministic or private input into the computation. And then there are actually different ways to mix and match. Let's say you can actually provide a program as a witness and provide just the commitment to the program as a public input. So we can think about this as like your initial state could be a commitment to the overall state of the VM. That's a public input. Your final state is also a public input. And then your program could be either a public input, or it could be kind of a commitment to a program, could be a public input, and then everything else could be provided as a witness. So this is kind of like a general model for the ZK virtual machine. So why do we why might we want to use a ZK virtual machine versus like a circuit, for example? So one of the things is, if you have this machine, the program that gets provided to the machine has nothing to do with ZK or cryptography in that sense. It's just, you don't really need to understand. You write a regular program that can be run on the VM. The VM handles all the cryptography itself. The second thing is it's universal in a way that if you have a Turing-complete machine, then you can basically execute any program on that VM. So you can execute arbitrary computations. You don't really need to do anything extra. The next one is, I would say, for the lack of better word, is simplicity. So there's a single, relatively simple set of constraints that describes the circuit of the VM. And that circuit doesn't change regardless of which program you execute on it. So just piggybacking on the previous talk, there is only one circuit that you need to verify and make sure that is correct. Everything else is just a program that gets executed by that circuit. So that simplifies a lot of things. And the last kind of benefit is recursion. So if you have a Turing-complete VM, you can write a program that can verify proof of its own execution. So you get basically infinite recursion, because if it can verify proof of its own execution, it can do it any number of times together with other programs that get executed. So these are very nice properties, and that's why in many cases a virtual machine is very desirable, like a ZK virtual machine is a very desirable thing to have. Now, there are some drawbacks as well. So one of the drawbacks is that a machine computation implies a certain structure. You want to have a repeated structure. You want to make sure that you have cycles that are described, and not all proving systems can handle it very well. For example, I think using R1CS, it would be very difficult to describe a virtual machine of this sort. Fortunately, for Starks, and specifically by Starks here, I mean air arithmetization plus Fry, but you really just care about the air arithmetization. So if you have air arithmetization, it's fairly easy to describe a virtual machine. And the second one is performance. There is a lot of overhead in the virtual machine. For example, you need to decode the program. You need to ensure, let's say if you have random access memory, you need to make sure that the memory access is consistent and all of that stuff. So there is quite a bit of overhead. And for simple computations, if you just need to prove, let's say, SHA-256 was executed correctly, then a virtual machine would be an overhead. The overhead would probably be much more than the actual circuit. There are some mitigating ways to address the performance. We can use specialized circuits that we can do lookups into and things like that. So it helps a lot. But again, if you have a very simple computation, you probably don't need a virtual machine if you really cared about performance a lot. All right. Let's talk specifically about Miden VM. So when designing this virtual machine, we need to make a few choices. Like the first choice is which ZKP system do we want to use? We use Starks, and not just Starks, but Starks with multi-set checks, which is kind of the technique that also Plonk uses a lot, where we can have different parts of the VM and we can like link them together. With array arithmetization, it's notoriously difficult to kind of have computations that are not uniform. This helps a little bit, well, actually not a little bit, quite a lot in that. The second thing is which prover to use. We use Winterfell prover. This is a general purpose Stark prover written in Rust, so it's very performant, so we've decided to use that one. Once we settled on the proving system and like the library that we're going to use, the next thing is which field do we want to use. With Starks, we get ability to choose small fields, which are not possible in many other proving systems. So for performance reasons, this Goldilocks field that Polygon 0 is using, and Polygon Hermes as well, is very, very performant. There are very fast reductions in that field, and also handling 32-bit arithmetic is very convenient in this field, because if you take two 32-bit numbers and multiply them together, they don't overflow the field modulus, so that helps a lot. And then the next thing is like which instruction set do we want to go with, and there are reasons why you would want to go, for example, with Ethereum virtual machine instruction set, or maybe like RISC-V or some other established instruction set. We decided in our case to go with something that is more ZK optimized. So we have RISC-V, for example, or EVM were not designed for ZK friendliness. When they were designed, nobody thought about how easy this would be to verify their execution in a ZK circuit or ZK virtual machine. So there are some benefits of using a ZK optimized circuit. We also use this MAST that I will touch upon. This is a Merkleized abstract syntax tree of how we represent programs. So this is also one of the reasons for us to choose a different architecture from what some other instruction set allow, or like some more established instruction set offer. All right. Let me cover like a few components of the Miden virtual machine. So first, as I mentioned, I think on the previous slide, it's a stack-based architecture. So you have a stack. We have a stack, and you kind of push the stack on, like it's very similar to, let's say, how WebAssembly works or how EVM works. You have a stack. We also have memory. This is a random access memory. It's a read-write memory. There are different considerations when you want to figure out like which kind of memory you want to use. For example, you could have a write-once memory or write-only memory, well, write-once memory, which will be very efficient in the cryptographic context. You need very few constraints to describe a write-once memory. Read-write memory is slightly more complicated, but we think the kind of trade-offs are worth it. In our case, we've designed it such that at every memory address there are 4 field elements. So if you think about it, 4 64-bit field elements, you basically get a 256-bit value at each memory address. I mentioned ability to offload computations to the specialized circuits. In our case, the specialized circuits are called chiplets. And for example, we have, I'll go over this, but for example, computing hashes. In our case, we use rescue hash as a hash function as the primary hash function within the VM, because it's arithmetization friendly, and there are many reasons why you would want to choose something like that. Would be, using something like SHA-256 would make the VM much, much less performant. And there are other chiplets. I'll cover them in a second. And then we have a concept of, we call it device provider. This is basically a way the VM reads non-deterministic inputs or secret inputs. You can provide anything from, let's say there's an instruction that says take a value from a device provider and put it on the top of the stack. And that basically means you can put anything, any value on the top of the stack. The device provider in our case is actually a bit more structured. You can actually read the entire Merkle path from a device provider, and that way to have like a Merkle proof. It's very easy to do Merkle proofs within the VM because we think that's a common use case. And since we have flexibility to design our instruction set, we can design like specialized instruction that says take the Merkle proof from a device provider and verify that it checks out against a given root and a given node value. So let me cover these chiplets a little bit more. So the first one, we have 16-bit range checks. These are used extensively within the VM. You need them for memory. You need them for 32-bit operations to you need them to, let's say if you want to break a given field element into two 32-bit values, or you need those range checks. So we have a dedicated component that does this 32-bit range, 16-bit range checks, and then we aggregate them in different ways. We have the hashing chiplet, which allows us to do like 2-to-1 hashes, the sequential hashes of field elements, and also verifying Merkle paths. So that's another it's a fairly, you can think about it as a mini processor of sorts, which allows you to do a bunch of different operations within that. And then bitwise operations, we cannot do them on the main processor itself, or it would be actually very expensive. So we do like AND and XOR. There is a specialized chiplet that does it. You can think about specialized circuit that does it, and XOR. We actually don't have OR. We emulate those with using just this one to keep simplicity, because from what we've done, like it's good enough to have these two. And this is, I know there is a lot on this slide, but this is the actual execution trace of the VM. In a stark context, you think about this 2x2 matrix, where each row is a state of the VM at a given clock cycle, and as the program executes on the VM, you actually add more and more rows to this matrix, and at the end you get to kind of the full execution trace of the VM. So, like logically, we break down the execution trace into different parts, so that you can see there is a program decoder that this is a pure overhead. This is just responsible for decoding the program and ensuring that the right program is getting executed on the VM. Then you have the part that handles the the operand stack. And then you have the range checker and other chiplets to the right there that handle memory and bitwise operations and so on and so forth. To give a couple of examples of how this actually works. So for example, let's talk about the stack. So the stack, in our case, I didn't draw the whole thing here, but it's like 19 columns. 16 columns represent like the top 16 elements of the stack. So let's say we initialize the stack to all 0. So like we wanted to execute a push 1 instruction. So what it does is just puts 1 in the leftmost column of the stack. Then there is a push 2. So it just the transition constraints for this are very, very simple, for example. And then you have an add that adds the 2. So like that's how the stack works, and this would be an execution trace of a stack component in the VM. Now, what happens if you need more than 16 elements in the stack? So for that, we have something that we call overflow table. And this is actually implemented using this multi-set checks, which allow you to kind of add things to that table. It's kind of a virtual table, what we call it, add things to the table, and then you use multi-set checks to verify the consistency of the table when you put things on it, when you remove things from it. So when an item doesn't fit in the top 16 slots, it gets added to the overflow table. When you drop something from the stack, the item gets moved from the overflow table back onto the top 16 registers of the stack, and so forth. To give another example, so let's say we want to hash something, and this is kind of like a very simplified example. So in the case of a hash, we have this RP hash instruction that computes, let's say, a 2-to-1 hash using rescue prime hash function. So you have some inputs and you have outputs, and you can see like the V values are the 8 inputs into the hash function, and the R values are the outputs. But we don't actually want to compute the hash as part of the stack trace. This is going to take a lot of effort and a lot of that kind of many cycles and so forth. So we have the specialized chiplet on the right-hand side, which basically it takes 8 rows in that table to compute a rescue prime hash, and some number of columns, obviously. So you can be guaranteed that like once you provide an input, let's say at row 0, at row 8, or actually at row 7, you will have an output. The issue is that they are not the same anymore. It doesn't happen in the same kind of in the rows that are next to each other. So one of the limitations of like pure air kind of arithmetization is that you only work with nearby rows. So here we need to use this multi-set checks again, where we have these buses, what we describe as buses, which allow us to, buses are implemented using this basically a single column, which is like a running product column, where whenever you put something on a bus, you multiply the value by like a randomized value of inputs, and then when you read something from a bus, you kind of divide it out of that column. So basically, the idea that you initialize this bus with 1, and then you write things to it, and you read things from it, and if you read in read exactly the same set of values, you end up with a 1 at the end. So that's kind of it's kind of our variations on this multiset, or kind of checks that we do. But it's very efficient. We only need 1 column to actually do communication between the stack and all the chiplets. We actually, in the whole VM, we have 2 bus columns. One is used for this type of chiplets, and then we have a separate column to handle communication with the range checker chiplet, just because there is also consideration of the degree of the constraints. And if we try to do it, like in our case, the maximum degree of the constraints in the VM is 9. So using just single bus column would have pushed us over 9, so we have to use 2 columns for that. Another thing, so I wanted to cover, so this is kind of like a general idea, and the same idea applies to all other chiplets, where you have like, your computation actually could, in a chiplet, could start in different cycles, so to say, but then we use the permutation checks to connect them. Another thing I want to cover is like how do we execute programs, because there are many different ways to provide programs. In our case, we have this assembly language, which we hope will have compilers to compile into this assembly language. And then assembly language then gets kind of compiled into this program MAST. And then this program MAST actually gets executed on the VM. So what is MAST? MAST stands for Merkleized Abstract Syntax Tree. And there are some key properties here, but the idea is that you build a binary tree, which where every internal node determines your control flow, and where every leaf node is just a linear sequence of instructions. And then the VM actually kind of traverses this tree in a depth-first fashion and executes each node according to its semantic. So eventually it will visit all the relevant nodes and execute them, and it will kind of, because it's a Merkle tree also, it will compute the hash of the program. So this hash binds the whatever instructions you executed on the VM to the actual program hash, so to say. So it's not just like there are other ways to hash the programs, right? You could just list out all the instructions and like hash it sequentially. In our case, there's a structural hash where you hash according to the semantics of the program. So to give a more concrete example, so let's say this is our assembly code. It's very simple. There is like some sequence of instructions, A0 through AI, and then we have like a, if the top of the stack is true, we execute B instructions. If the top of the stack is false, which is like 1 or 0, we'll execute C instructions, and then at the end we execute like some sequence of D instructions. So a program MAST for this would look like something like this. To kind of explain a bit more, we have these join blocks and split blocks, or nodes, we can call them. So a join node basically means that you execute both left and then the right child. And a split node, that means if the top of the stack is 1, you execute left child. If the top of the stack is 0, you execute the right child. So that's how you do it. We also have loop nodes. I didn't go into how loops work here. But basically, you can see from this, so like if you traverse this tree in a depth-first manner, so you first would execute the A0 through AI, then you will kind of go back up, and you will see that this is a join node, so you need to execute the node on the right. So you'll execute B0 through BI if the top of the stack is 1, and if not, you'll execute the C, and then you go up to back to the top, and then you execute the D instruction. So one question is, why do we bother with MAST? Why didn't we do something that is kind of just hash the entire program and do it this way, or provide the program as a public input? There are a few good reasons for that. So one of the reasons is efficiency. So if your program is large and you want to provide it as a public input, that puts a lot of pressure on the verifier and also like on the prover itself. So it's you don't want to provide the program as a public input if the program is large. You can provide just the sequential hash of all the instructions, but that means that regardless of which path in the program gets executed, you need to always hash the entire program. But like basically, we unhash the program inside the VM. Like we provide the actual program non-deterministically, but you need and then hash it to make sure it matches provide the public commitment. So if you have a smart contract, for example, with a bunch of functions, regardless of which function gets executed in a given transaction, you need to unhash the whole thing. With MAST, you don't need to do that. You effectively unhash only the executed path of the in the Merkle tree or in the MAST. There is some aspect of safety to it. So like with this approach, you can't actually write self-modifying code, because everything is fixed by, like once you hash it all together, like everything is fixed by hash. You can have dynamic jumps. All the call targets needs to be statically known. And like it's actually an interesting model. When you make a function call, you don't make a functional call by reference, you make it by hash. So you actually, when you make a call, you know exactly which program is going to be executed because it is committed to by the hash value of the function that has been called. And then there is some aspect of privacy to this as well. So you can have, in this Merkle tree, for example, you can say, I'm going to reveal part of the program, like let's say, the leftmost nodes and the rightmost nodes, but I'm going to keep the middle secret. This way, when I execute the program, I actually need to know the whole thing. But when I verify the program, I just need to know which one was the precondition and which one was the post condition. But I just need to know the hash of whatever was in the middle. I don't actually need to know the full program. So yeah, I think that's pretty much it. And I think I managed to do it in 20 minutes.
Kind of a high-level question. So there are a lot of different projects now that implement their own VM or design their own VMs. I guess there are like 5 or 6 VMs now.
Yep.
How do we think about comparing them? Like, are some of them good for some applications and some good for others, or does some dominate others in one way, one way or another? So how do we compare these
Yeah,
VMs?
definitely. I think, I mean, there are many different metrics on which we can compare them. For example, there are several projects that are doing ZK VM. So the rationale there is that we have enough developer tools that are developed. Like it's going to be a more complicated VM to build because obviously, the set of constraints that you need to describe is much, much higher than something like Miden requires, for example. But you have access to different developer tooling. So if you want to prioritize like being people not having to learn things, then you want to go with
But I'm comparing it to Cairo or to PIL or.
Another dimension is like how easy it is to implement. So, for example, Cairo is very, very simple. It requires, I think 2 pages to describe the constraints for Cairo. So the constraints are super simple. In case of ZK VM, I think constraints are really, much more complicated because, again, you didn't have the flexibility to design it. And Miden would fall somewhere in the middle, where more complicated constraints than Cairo, but much simpler than ZK VM. So. I guess it really depends on what you want to optimize for. So if you want to optimize for cryptographic simplicity, right? Like the Cairo approach is one. Like that's the one that is like probably the most efficient. If you want to optimize for developer, kind of like being able to like use the VM without learning new things, then like ZK VM or like RISC-V instruction set, because there are a bunch of tools available, that might be another one. If you want your VM to be used in a blockchain, for example, like RISC-V might be a good instruction set, but it's not tailored for blockchains, for example. So you might use RISC-V in the situations where you maybe don't need to rely on blockchains as much. But if you want the blockchains, you might need to add some special instructions or something like that to the VM that make things more efficient. Like we want to be able to verify signatures very cheaply. Like with an EVM, there is like a very simple way to do that. Hopefully we'll have the same way in Miden. But general purpose, kind of like if you did like WebAssembly, for example, build a VM that verifies WebAssembly, can execute WebAssembly. It may not be well suited for a blockchain context. So I guess there is like complexity of implementation, developer friendliness, or like a set of availability of tools and like your use case. So those are the different metrics. And I think different VMs are trying to address those in different ways.
Great, thanks. Really awesome work.
Thank you.
All right, since we are running a little bit over time, we're going to cut questions here and introduce our next speaker, Ayush.
Thank you.